Okay, great. So, hi, I'm Moshe. I'll speak about fair shares, feasibility, domination, and incentive. This is a joint work with Uriel Feige. Okay, so we're interested in fair partition of indivisible goods when we cannot use money. So in this example, we have two agents. They need to partition these items between them without any transfers. So what would be a fair allocation? So there are two approaches in general. One is to try to eliminate or minimize envy. And the second approach, which I'll take in this talk, is to try to give each agent the value that she deserves or close to it, or the share-based approach. And that value will be with respect to her own valuation function. Okay, so what's the model? We have n agents. They are equally entitled to a set of indivisible items, and there is no money. Each agent has a valuation function mapping subsets to a value. And sometimes I'll discuss additive valuations, but not all the results are for additive. And we are seeking for an allocation, which is a partition of the items to the agents, a deterministic allocation that is fair. Each agent I gets some bundle AI. Okay, so Budish has suggested the notion of Maximin Share, which is the highest value that an agent can insure herself by splitting the items into n bundles and getting the worst one. In this example, with an additive valuation, the value of the Maximin Share when there are three agents is 2. Clearly, sometimes it's not possible to give every agent more than her Maximin Share. For example, when the valuations of everybody are identical, the Maximin Share is exactly by definition the maximum that we can get any agent, all the agents concurrently. Okay, so is it always possible to find an allocation that give every agent her Maximin Share? So in a celebrated result, it was shown that for additive valuations and even three agents, it is not possible. So there are some valuations for the three agents for which it is not possible to give every agent her Maximin Share. And the terminology that I will use is that the Maximin Share is not feasible. That is, there exist valuations for which we cannot give every agent her Maximin Share. Okay, so I would argue that if it's not feasible, we cannot use the Maximin Share as a fairness guarantee, because a guarantee is actually something that you know for sure that you will always get. So we want to define general notions of shares and look for good share, a good share that is always feasible. So for example, the zero share is always feasible, but it's not good. So I need to define what do I mean by a share and what do I mean by a good share. So before that, let's look at the landscape of shares. There are all these shares, for example, the Maximin Share and the proportional share that was presented before. And there is the set of feasible shares. These are shares that we can always give to every agent. And the Maximin Share is always as large, at least as every feasible share, as we discussed, because you can never give every agent more than the Maximin Share. So this will be denoted by this arrow that says the Maximin Share is at least as large as any feasible share. Okay, so what is a share? An abstract share is a function S that maps a valuation of the agents Vi and the number of agents N to a non-negative share value S of Vi and N. Note that this share definition is a function only of Vi and not the valuations of the others, and can be computed essentially from the knowledge of the agency herself. Note also that the S is not indexed by I, so we're using an anonymous function, and this is supposed to capture the fact that all agents are equally entitled in the first place, as there is no reason for the share to be defined differently for different agents. So given a share definition, we want to use it as a fairness guarantee. We define a bundle B to be acceptable to agent I if she gets at least her share. So the value of B is at least the share. And the share guarantee is the minimal value of all of the lowest acceptable bundle. So we go over all bundles that are acceptable and consider what would be the minimal value. That is the share guarantee, what the agent can perceive as she is always going to get if she's getting her share. So we view a share as kind of a contract between the agents and the allocator. The contract gives the agent the right to get an acceptable bundle, a bundle that gives her at least her share. while the allocator still have the flexibility or the right to choose which acceptable bundle he wants to give each agent. So the first property ensures that each agent has some fairness guarantee, while the second property ensures that the allocator still have some flexibility to achieve other goals. So what are the desired properties from a share? So first, we want it to be feasible because we want to be able to give every agent at least her share. Second, we want the agents to be able to check if the contract is satisfied. That is, given your bundle, could you tell if the bundle gives you your share or not? For that, the share should be polynomial time computable. And finally, we want incentive for truthful reporting. And this is notion that is we call self-maximizing, and is somewhat related to the notion we have seen in the previous talk. The idea is that I'll explain that in details, but we want agent to be truthful such that the share will be computed with respect to the correct valuations. Okay, so what is a self-maximizing share? Recall that we let the allocator choose any acceptable bundle, any bundle that give an agent her share. So will the agent report her valuation truthfully? So we're going to assume that the agent wants to maximize her share guarantee. That is, given the share function, she wants to be sure that she'll get the maximal value, which is essentially kind of very strong risk aversion again. So definition is the share is self-maximizing if truthful reporting maximizes the share guarantee. And of course, this is measured with respect to the truth. And I'll explain it with an example in a second. Okay, so first let's consider the Maximin share. The Maximin share is the worst bundle out of all n bundles. Clearly, there is no reason for the agents to manipulate the partition and suggest the partition not according to her true valuation, because at the end of the day, she's going to get a bundle that is the worst compared to her true valuation. So the Maximin share is actually self-maximizing. But the literature also considered an approximation to the Maximin share. For example, the 3/4 Maximin share is known to be feasible. We can always give every agent her Maximin share, but let's consider whether it's self-maximizing or not. So we have an additive valuation over these three items with value 100, 80, and 20, and n equals 2. There is, of course, a partition of to two bundles of value 100, so the value of the Maximin share is 100, and 3/4 of that is 75. So what is the share guarantee? The share guarantee is the value of the minimal bundles that is at least 75, which is the 80, the shares by themselves. Now let's consider the following manipulation by the agents. Instead of reporting 100, 80, and 20, she reports 100, 50, and 50. We can see that the same partition gives us a Maximin share of 100, so the 3/4 Maximin share is still 75. But the shares by themselves no longer guarantee the share value. So now every bundle that gives at least 75 include a value of at least 100. So that is a beneficial manipulation by the agent, which show that the 3/4 MMS is actually not self-maximizing. So to summarize, we saw that the Maximin share itself is self-maximizing, while the 3/4 MMS is not self-maximizing. Okay, so let's go back to this landscape of shares. The 3/4 MMS, which is known by the result of Grag and Taki to be feasible, is actually not self-maximizing. The Maximin share is self-maximizing, but not feasible. Okay, so let me discuss briefly the difference between self-maximizing and the usual incentive compatibility in dominant strategy. So for dominant strategy, the allocation algorithm is actually fixed, while for self-maximizing, the allocation algorithm is unknown. We just know that the allocation that will be given to the agent will give her her share. In a dominant strategy truthfulness, reporting VI is give you the best allocation for any valuations V minus I, while in the case of self-maximization, VI will give you the best guarantee. That is the maximal share guarantee over all algorithms and valuations of the others, which is essentially kind of very strong risk aversion. Okay, So once we define shares, we can think about domination. So what's a domination? We look for a feasible share that is the best possible, because if we can find such a share, our search for shares, for good share, will be done. Okay, so let's define this partial over shares. We have a share S and it dominates S prime if for every valuation in the class of valuations, the value of the share for V is at least the value of the share S. The value of the share S for V is at least the value of the share S prime for V. Now we have a partial order over shares. We can think about the dominant feasible share, which is a maximal element in this partial order, one that dominates every other share. And a subset of these shares are the shares that are feasible and self-maximizing. So an SM dominant feasible share is a share that dominates only the feasible shares that are self-maximizing. That's a weaker requirement. And the question is, does there exist an SM dominant feasible share for the class of additive valuations and for other classes? So let's look at this landscape of feasible shares. 0 is a share that is self-maximizing and feasible, and we can consider other shares that are feasible and self-maximizing, and there is this set of all shares that are feasible and self-maximizing, and we are searching for a feasible share, a share that is that SM dominate every other feasible and self-maximizing share. That would be an SM dominant feasible share. So let me move to our results. So for this question of finding such an ultimate share, we actually prove that for any class C that contains the additive valuations, there is no feasible share that dominates all feasible shares that are self-maximizing. So not only that we cannot dominate all feasible share, even if we restrict ourselves to try to dominate only the self-maximizing share, that is impossible to do. So there does not exist an SM dominant feasible share for class C if C includes the additive valuations. So there is no ultimate feasible share. For any share, we'll be able to find some other share that, at least for some valuations, is larger. So let's go back to our landscape. There is no SM dominant feasible share. Okay, so let me briefly discuss this result. First, note that we are not requiring the dominating share to be self-maximizing itself, which strengthens this impossibility result. And secondly, this impossibility result does not rely on computational hardness. It is unconditional on any computational issues. And in the paper, we actually present two proofs for this result. The first one is explicit in the sense that we construct some shares, which we call the picking order shares, and prove the result using these shares. I will not have time to discuss these shares, but you're welcome to look at the paper. And the other proof is actually using a result that I'll present next, and I think is of independent interest. So let's start from any share that is feasible. One might wonder whether there is a self-maximizing share that actually dominates it. And this theorem proves the following, that for any share S that is feasible, there is another share S prime that dominates the first share, and it's also self-maximizing. So in some sense, requiring that the share is self-maximizing is without loss of generality, but that's not exactly the case, because actually this transformation is not polynomial time computable, even if the evaluations are additive. And this will play a role in the next part of the talk. Okay, given this result, let me prove to you that there is no ultimate feasible shares for additive valuations. So let's define for every valuation VI a share S of VI as follows. The share value equals to the MMS on VI for the valuation VI itself, and it is 0 for any other valuations V prime. So clearly this kind of share is feasible, because if all the valuations are VI, we give every agent her MMS, and for any agent that has a different valuation, we don't need to give her anything. So this is a feasible share, and the theorem claims that there is another share S prime of VI that dominates S of VI and is also self-maximizing. Now clearly this share for the valuation VI needs to give the agents at least the Maximin share. Now, in order for a share to be an SM dominant share, the share needs to dominate every S prime of VI, which means that it needs to dominate every S of VI, every share S of VI, but the Maximin share is not feasible for additive valuations, so there does not exist a share that dominates every share S of VI. So this completes the proof that an ultimate share does not exist for additive valuations, and we actually prove it also for shares that are beyond additive. So let's summarize this impossibility result, that for class C that contains additive valuations, there is no feasible share that dominates all feasible shares that are self-maximizing. So given this impossibility result, we relaxed the notion of domination to raw domination. So we said an ultimate feasible share does not exist, so let's consider raw dominating every other share. So what does it mean? It means that we take another share, we scale it down by a factor of raw that is smaller than 1, and then we want to dominate the result. So a raw dominating share is a share that raw dominates every feasible share, and we want to find some raw dominating feasible share that is polynomial time computable and feasible. So observe that a share is a raw dominating feasible share if and only if it raw dominates the MMS. That's actually quite easy to prove. And so for example, the 3/4 MMS, as the MMS dominates every other feasible share, the 3/4 MMS raw dominates every feasible share for raw equals 3/4. Okay, so we said that we cannot use the MMS because it's not feasible. Why can't we use a raw MMS? We basically said that even for 3/4 MMS, which is feasible, it is not self-maximizing. And actually, we prove in general that for any raw that is smaller than 1, the raw MMS is not self-maximizing. And this is the example that proved that result. So what we actually want to find is a raw dominating feasible share that is self-maximizing and polynomial time computable for large value of raw. So let's go back to this landscape of feasible share. We add polynomial time as a requirement and search for a share in this intersection of feasible share, maximizing share, and polynomial time shares. And we want to find such a share that raw dominates every share in this green circle. Every feasible share will be dominated, raw dominated by these shares that we are after. Okay, so what do we show? So the main result in this paper is that for class of additive valuations and N agents, there is a share which is called the nested share, which I'll present in a second, that is feasible, self-maximizing, and polynomial time computable, and it is about 2/3 dominating. So if we scale the other share by factor of 2/3, then we dominate that share. If the number of agents is small, say up to 4, we can actually improve the constant to 0.8. And for agents and any positive epsilon, there exists a share that is feasible, self-maximizing, and polynomial time computable, and it's 1 minus epsilon dominating. So note that the Maximin share itself for 2 agents is actually feasible and self-maximizing, but it's not polynomial time computable. And the MMS is NP hard, so actually if we want to have polynomial time computability, we need to relax it to 1 minus epsilon. Okay, so what is the nested share?
Real quick, we're at time, so you might, we'll need to move on quite soon.
Okay, great. So I'll just say a few words about the nested share and I'll wrap up. So the nested share are basically a relaxation of the Maximin share in which we restrict the set of partitions to be partitions in which items are sorted, and we take bundles constructed from some items from the prefix and from the suffix. And we prove a result for the nested shares that have some conditions that the prefix has singletons, and you're welcome to ask me later about that. So let me just wrap up. So we initiate a systematic study of feasible shares. We suggest this notion of self-maximizing share and show that any feasible share is dominated by a self-maximizing and feasible share. We prove that for additive valuation, an ultimate feasible share does not exist, one that dominates all feasible shares that are self-maximizing. and we present raw dominating feasible shares that are self-maximizing and polynomial time computable for additive valuations, with a p-task for 2 agents and a constant for more agents. And then maybe the most interesting open problem is obtain a row of 3/4, which is the best thing that we can know how to do without the requirement of self-maximization. So thanks.
So we have time for one question before Paul sets up his. So any question? Yes, please.
Moshe, does the set of self-maximizing feasible shares have a maximal element? One that's not strictly dominated by any other?
Sorry, I couldn't hear that.
Oh, I was wondering if the set of self-maximizing feasible shares has a maximal element, which is not strictly dominated by any other.
Yeah, so this is a partial order. So I guess the question was whether this partial order has a maximal element. I suspect it does, but I'm not sure. I think that this partial order has possibly multiple maximal elements. The only reason you might not have a maximal element is because of infinite number of elements, right? But so I suspect there should be some maximal elements, but we did not prove it in this paper.
Okay, let's thank Moshe again.
Okay, thank you.
And let's clap again real quick for our first presenter, since we didn't have the other there. Let's keep it even.
So